Welcome back, curious minds, to the second installment of our volcano series. In part 1 we covered the fundamentals, what a volcano is, the basic types, and why they matter. Today we dive far deeper, exploring the ancient origins, the intricate science, and the cutting-edge research that defines modern volcanology. We begin with the origins of volcanic activity. Over 4.5 billion years ago, as Earth cooled from a molten state, the first upwellings of magma pierced the nascent crust, forming the primordial volcanoes that spewed basaltic lava across the early landscape. Ancient civilizations recorded eruptions in stone tablets, but it was the geological record that revealed a timeline stretching back to the Archean, when the planet's interior was still churning with primordial heat. These early eruptions helped shape the continental crust, providing the building blocks for the continents we inhabit today. Moving from history to mechanism, we examine how plate tectonics drives volcanic processes. At convergent margins, oceanic plates plunge beneath continental plates, releasing water into the mantle wedge, lowering the melting point and generating silica-rich magma. Divergent boundaries, such as the mid-Atlantic ridge, allow mantle material to rise and decompress, producing basaltic lava that creates new oceanic crust. Meanwhile, mantle plumes, immense columns of hot rock, rise from deep within the mantle, forming hotspots like Hawaii, where a stationary mantle source creates a chain of volcanic islands as the tectonic plate drifts overhead. The chemistry of magma is a delicate balance of temperature, pressure, and volatile content. As magma ascends, dissolved gases, primarily water vapor, carbon dioxide, and sulfur dioxide exsolve, forming bubbles that expand dramatically. This degassing process is the engine of explosive eruptions. High silica magmas become highly viscous, trapping gases and leading to catastrophic pressure buildup. When the containment fails, the result is a Plinian eruption, ejecting ash and pumice kilometers into the stratosphere, as witnessed at Mount Vesuvius in 79 AD and more recently at Mount Pinatubo in 1991. Conversely, low silica basaltic magmas flow freely, creating gentle lava fountains and extensive Awithmakron or Pahoehoe flows that reshape the terrain over months or years. Understanding these dynamics is not merely academic, it underpins our ability to forecast volcanic hazards. Leading experts such as Dr. Catherine Cashman have pioneered the study of magma rheology, revealing how crystal content and bubble dynamics control eruptive style. Dr. Clive Oppenheimer's interdisciplinary work integrates satellite remote sensing, seismic networks, and gas spectroscopy to detect subtle changes in a volcano's behavior. Long-term observation stations on Mount Etna, Kilauea, and Soufriere Hills have amassed decades of data, showing that increased seismic tremor, rapid ground uplift, and spikes in sulfur dioxide emission often precede an eruption by weeks to months. These indicators allow authorities to issue timely evacuation orders, saving lives and reducing economic loss. Yet the significance of volcanoes extends far beyond immediate hazards. Volcanic ash clouds can ground transcontinental flights, as the 2010 eruption of Iceland's Geological demonstrated, disrupting millions of passengers and costing billions of dollars. Sulfur dioxide released into the atmosphere forms sulfate aerosols that reflect solar radiation, temporarily cooling global temperatures, a phenomenon that contributed to the year without a summer after Pinatubo's eruption. Moreover, volcanic soils are among the most fertile on Earth, supporting agriculture in regions like the Andes and Java. In a changing climate, melting glaciers atop volcanic peaks may increase pressure on underlying magma chambers, potentially triggering renewed activity at volcanoes previously considered dormant. This emerging risk underscores the need for continuous monitoring and international collaboration. As we conclude this deep dive, remember that volcanoes are both creators and destroyers, shaping landscapes, influencing climate, and challenging humanity to understand Earth's inner workings. In Part 3, we uncover what mainstream sources won't tell you.